When treated with two equivalents of an alcohol, a ketone or aldehyde can be converted to the corresponding acetal. Much like hydrate formation, which was the previous video in this series, this reaction entails nucleophilic addition across the carbonyl. However, in this case, the process occurs twice. The reaction requires catalytic acid and is freely reversible. The position of equilibrium is often controlled by adding excess alcohol in order to push the reaction toward the acetal, or alternatively, an acetal can be hydrolyzed using excess water. And these are both examples of exploiting Le Chatelier's principle to control the position of equilibrium. Acetal formation begins with the protonation of the carbonyl oxygen. This enhances the electrophilicity of the carbonyl carbon, making it more receptive to the attack of an alcohol. This pushes the carbonyl pi bonding electrons onto oxygen to neutralize its charge. The new oxonium ion formed from this attack readily loses a proton to produce a reaction intermediate that is known as the hemiacetal. When the hemiacetal is protonated on the hydroxyl oxygen, a good leaving group is produced, and water therefore dissociates. This results in the formation of a carbocation that is resonance stabilized. The positive charge can be delocalized onto oxygen, resulting in a more stable resonance form in which all atoms have a complete octet. A second molecule of alcohol then attacks this cation, and loss of a proton ultimately results in the acetal product. The hydrolysis of an acetal occurs via the exact same mechanistic steps. They simply occur in reverse. In other words, the acetal can first be protonated on one of the alkoxy groups. This activates one of those groups as a good leaving group, and dissociation of that alcohol affords a resonance stabilized cation. Water adds to this resonance stabilized cation, and the subsequent loss of a proton from the intermediate oxonium ion affords the very important reaction intermediate known as the hemiacetal. As we saw previously, this is the midway point between the acetal and the original carbonyl containing molecule. Protonation of the hemiacetal on the remaining alkoxy group makes another good leaving group, and dissociation of that alcohol affords a resonance stabilized cation. The more stable resonance form delocalizes the positive charge onto the oxygen, and this is the more stable resonance contributor because all atoms possess a complete octet. Loss of a proton from this resonance form regenerates the original carbonyl containing substrate, which in this case was a ketone. Let's turn our attention to a specific example in which acetone is converted to its dimethyl acetal by treatment with at least two equivalents of methanol. If excess methanol is used, the equilibrium will favor the dimethyl acetal, and that acetal's formation begins with the protonation of acetone's carbonyl oxygen. This makes the carbonyl carbon more electrophilic, so methanol attacks the carbonyl carbon, pushing the carbonyl pi bonding electrons onto oxygen. The new oxonium ion that results sheds a proton to the medium to afford the hemiacetal. When this hemiacetal is protonated on the hydroxyl group, water can dissociate as a good leaving group. This yields a resonance-stabilized cation that is attacked by a second equivalent of methanol. And a proton is subsequently lost from the oxonium ion that is formed to generate the final product of the reaction, the dimethyl acetal of acetone. If we were to treat this dimethyl acetal with catalytic acid and excess water, it could be converted back to acetone. And this process would begin with protonation of one of the alkoxy groups. This activates it as a good leaving group, and so methanol subsequently dissociates. The resonance-stabilized cation that results would be attacked by water. And this generates an oxonium ion that sheds a proton to the medium to afford the critical hemiacetal intermediate. When it is protonated on the remaining methoxy group, the hemiacetal can experience the dissociation of a second methanol molecule. This generates another resonance-stabilized cation, which loses a proton to reform acetone. It is also common to encounter cyclic acetals, which are formed from the reaction between ketones or aldehydes and a diol, such as this one. The mechanism for this reaction is absolutely no different than the mechanism we have considered thus far. It is merely the fact that the two alcohols are now tethered together that results in the formation of a cyclic product. Acetal formation still begins with protonation of the carbonyl oxygen. With the electrophilicity of the carbonyl now enhanced, the carbonyl carbon readily accepts the attack of an alcohol, and the oxonium ion that results loses a proton to generate a hemiacetal. When the hemiacetal is protonated, water is formed as a good leaving group and dissociates from the substrate. This forms a resonance-stabilized cation, which is attacked by a second alcohol as it would be in any other case. It's just that now that second alcohol is already tethered to the substrate. A ring results from this attack, and the oxonium ion loses a proton to form the cyclic acetal. The hydrolysis mechanism for cyclic acetals is also directly comparable to that which we have seen previously. The acetal is first protonated, and the good leaving group that results dissociates. The resonance-stabilized cation accepts the attack of a molecule of water, and the loss of a proton from the oxonium ion generates the hemiacetal. When the hemiacetal is protonated on its alkoxy group, the diol can then dissociate as a good leaving group. Loss of a proton from the cation that results regenerates acetone. In summary, acetals are formed when ketones or aldehydes are treated with catalytic acid and excess alcohol. When the hydroxyl groups are tethered in a diol, a cyclic acetal results. And any acetal can also be hydrolyzed by exposure to catalytic acid and excess water. The ability to readily form and remove acetals makes them ideal protecting groups in synthesis. For instance, the ester of the keto ester shown here cannot easily be selectively reduced. Reducing agents that are powerful enough to reduce the ester will also reduce the ketone present in this substrate. This problem can be solved by protecting the ketone as an acetal. In this instance, we chose to treat the substrate with a diol, ethylene glycol specifically, and catalytic acid, and that results in the formation of a cyclic acetal. With the ketone thus masked and unavailable for reaction, the ester can be reduced with lithium aluminum hydride. During the aqueous acid workup of the lithium aluminum hydride reduction, that was step 2 on the previous slide, the ketone will also be unveiled through the acetal hydrolysis mechanism that we learned in this video. This affords a product in which the ester has been selectively reduced to the alcohol and the ketone has been unaffected. As was stated at the outset of this problem, the direct reduction of the ester in the presence of the ketone would have been very difficult. However, we have now seen that formation of the acetal protects the ketone, allowing the ester to be reduced with lithium aluminum hydride, and then during the aqueous acid workup of that reaction, the acetal is cleaved to unveil the ketone, and so through a circuitous path we have managed to selectively reduce the ester in the presence of the ketone. The preceding was an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, or in paperback at a discounted price from Lulu.